It's always an absolute pleasure having Andy Farnell present to us. He's one of our most popular lecturers. I think your procedural audio video is up at 15,000 views on our YouTube channel, which is quite impressive. Mine's only at like 150, so that gives you some scale. Andy's a visiting professor at many universities around the world and a pioneer in procedural audio. And we're going to learn about something completely different. So over to you.
Thank you very much, Charlie. Thank you for inviting me along this evening. It's a real pleasure to be back in London. It's actually kind of almost been 2 years. As some of you know, I became a dad 2 years ago, and it was the same time I stepped down from the committee, and about the same time I left London and my teaching duties at SAE and at Queen Mary and other places. So I've kind of been having a hiatus of it was at least 18 months, just doing little bits of consultancy and taking my little girl to the beach a lot. So it's been great. But in order to keep putting bread on the table, I took up a short teaching post as an associate at Solent in Southampton. And I'd like to present some of the work that we've been doing at Solent to you this evening. Partly because there's some comments mixed in with this about directions that are happening in higher education. And I know many of you are involved in teaching, and I think Rupert was telling me he's a STEM mentor now. And things are always changing in education. Resources seem to be getting fewer and fewer. We're getting squeezed in so many ways. Hi, Nick. So what I'd like to present is this is called our shoestring theory of physics teaching, is what happens when you're told that your budget for a level 6 module in HE, which involves practical work and manufacture, is £15 per head, which is kind of enough to go to the pub with, but not enough to do really much more. The talk tonight's really intended to be a little bit of fun. I didn't want to do anything terribly serious, and so this is what we've been doing. Who's aware of the Toaster Project? Have any of you come across the Toaster Project? So Thwaites, there's a YouTube video of it, and it's very interesting. He started in 2008 with this challenge, which was a bit like a kind of survival island type scenario. Imagine you have no resources at all and you need to build a toaster. So you can't order the bits from, you can't order the bits from Maplin anymore because they're not there, from Radio Spares. You can't go down to the hardware shop and buy the stuff. You need to make everything from the ground up, which includes the manufacture of metals, attempts to make plastic. It's actually odd because a toaster is a bizarre 20th century device anyway. If you wanted to toast bread, you just put it on the fork and hold it by a fire, right? But the actual artifact of a toaster, it turns out it had like several hundred moving parts. Several hundred parts of which like at least, I think 20 or 30 were articulated in some sense. Various springs, connectors, contacts, mechanisms to hold the bread in place. So it's all documented here in this book in Princeton, and a great video of it. Of course, this is the results. I think it lasted like about 12 to 15 seconds or something. Burst into flames. Technically, it toasted one piece of bread, and then that was the end of it. So the last comment here. It's something a little bit serious, maybe. There was I think it was a Union of Concerned Scientists, or a similar group, who kind of listed a bunch of great threats to humanity. And amongst those are things like AI, global warming, and so on. A very controversial and interesting list. But one of them is this, kind of call it the problem of the pulled up ladder, is that when we're no longer able to bootstrap ourselves as a civilization, the knowledge in order to do many basic things has disappeared. If you think whole bodies of human knowledge, think about, say, thermionics. Who's ever built a power amplifier or a radio or anything using valves. Okay, and that's probably, I'm imagining that was representative. I thought maybe half of you, whatever. But look, for the younger ones here, we haven't ever had the pleasure of 450 volts across your hand. But if you think about it as a body of knowledge, that's kind of disappeared now. There's really no need, except in bizarre safety-critical sort of nuclear situations, to use thermionics anymore. So that whole discipline has kind of vanished. And so have other huge tracts of human knowledge. And what they mean is that it's no longer possible for us, given a kind of catastrophic reset situation, even though the books are there in the libraries, the understanding of those books and the praxis of putting them, into manufacturing is not there. And so what I find these days from younger students is, well, let's just call it a very cavalier attitude towards technology. Very embracing of it and accepting, but really it's effectively magic. And that's worrying. So I think many of us who have kind of gained full spectrum knowledge in our disciplines, maybe for me in computing, and for many of you in electronics and acoustics and so on, is that you can't see a way that a young person could actually take on board the entire spectrum of the knowledge now. And to some extent, they're not interested. Anyway, let's move on. This is my current situation. I was very lucky that Professor Barlow, Chris, invited me to come on board at Solent. There's a lovely, small, vibrant team, and our acoustics course is, little plug, it's absolutely brilliant. We've got some nice bits and pieces here. Let's put the laser where the laser should be. There we go. So we've got an interferometer looking at displacement on this in one of our chambers. We've got a small chamber and a slightly bigger one. I was asked to teach electroacoustics, which is transducer technology. That's actually a level 5 unit, which is, what shall we say, everything to do with turning energy into signals and signals into energy of one kind or another. I had 20 bachelor students. Before me, I had a lovely set of notes given to me by Christos, and I kind of reworked those into much more of a practical syllabus. I've got Ludo and Matt working with me down at Solent, and so we've got a lovely little setup for teaching acoustics. Hi, come on in. Okay, so what's on the course? We're looking at really three areas of physics, being the electromechanical physics, everything that changes acoustic energy into a change in conductance, really change in resistance. Electrostatics, which is various forms of charged plates, membranes, and so on. So we're looking at displacements turning into changes of movements of charge. And the classic stuff in electromagnetics, which is sort of winding coils and magnets and so on. So we're looking at it from two sides. Loudspeakers of the latter two categories, and microphones in all three of those categories, in electromechanics, statics, and electromagnetics. And the final one is the solid state stuff with piezo crystals. It's very easy to go and buy these little discs, and people use them in everything. But I've been fortunate enough to have some experience with experimenting with piezo technologies in several other areas. And I don't know if you're aware, there are all kinds of fascinating new materials which have piezoelectric properties, both output, and they can be used as a large edge-supported membrane, or they can be kind of put into composites to become embedded microphones inside things, incredible vibration detection with things like polyvinyl fluoride and stuff like that. So lots of fun to be had with this. As well as that, we've got the kind of coupling of these transductive systems into acoustic space and from acoustic space, so various sort of horns and acoustic levers. This is the stuff, okay. In addition to that, we look at some of the signal flow in between. So but remember, these guys have not got good electronics knowledge. So they've maybe seen an op-amp before. They've maybe seen a single-stage transistor amp. So we're going to possibly put a preamp and a power amp at the output. An absolute gift these days is, single-chip systems like the LM360 something. It's a little 1 watt 8-pin dip. And you can just stick that in and get 1 watt of output from it. It drives most things. Although I chose 2 really standard classic texts for this, which I think that perhaps the maths was a little bit above some of those on level 5. But any of Harry Olsen's stuff is absolutely fantastic for transducers. There are several more modern texts, but I haven't much to say about them at the moment. Right, so here's how we got to this project. I was told that we had, I think, was it 6 hours on a weekly basis, of which 2 were going to be lecture-based and 4 were going to be practical. And there's a great opportunity in acoustics, obviously, for different blended learning methods and for project-based learning, where you go and design something and make it. So I thought, great, we've got this incredible manufacturing facility there because we teach engineering design. We have laser cutters, plotters, etching baths. We have TIG welders, MIG welders, various forms of 3D printing, all sorts of great stuff. Maybe I was going to say surprise, was that we weren't allowed to use any of that because it belongs to a different department. So acoustics, this is what we could spend our £15 on. Miles and miles of enameled copper wire, great. Paper plates, string, fishing wire, tin cans. We actually robbed most of the paper cups from the coffee shop. They're very good, sturdy paper cups, brilliant for making all sorts of things. Some packets of strong neodymium magnets. That's the magic. They make everything work. If you're going to embark on this path, you need to, a pack of the smallest, most high-density flux ones that you can get. And they're really hard to order because they send them in the post and they come in a great big thing, and you unpack them because they'll just stick to everything. They're amazing. Foil balloons. So it turns out that many of those big silver party balloons that you get, there's a reason why you shouldn't let them go near electricity pylons. They are properly conductive. You can put the meter on them from one side to the other and it's reading about 10 ohms. So they're metallized on the top of that plastic, which is great. Wooden embroidery hoops, amazing for edge supporting any material to experiment with. Elastic bands, tape, glue, scissors, blades, some little 1 watt op amps, and off we go. So you get the message here that we're basically really doing this on a budget. Okay. Problem number 2 is we don't have a great workshop. We're near to a workshop which we can sneak into from time to time, maybe to hold something in a vise or borrow a little bit of PVA adhesive. But really, we're kind of down to hand tools. And one of the absolute godsends was us finding an electric drill, which you'll see was absolutely necessary for winding some coils. Okay. I think I've already mentioned this compartmentalization, by which I mean that we weren't allowed to use the facilities even though they were visible through the window next door. Obvious health and safety issues. I'm not going to poo on that too much because it's good. There's plenty of common sense, and we were given quite a long leash. And these, they're adults, right? Our students are adults, so safety goggles for etching, pretty important. High voltages. One of the real pains was we were limited to 30 volts. All the power supplies, you could actually, I taught them a trick of getting 2 power supplies, and so we could get 60 volts, you know. But, you know, we were limited to 30 volts, which is a troubling when you're trying to make capacitor microphones. And another problem was having a shared lab. So we were in something called the instrumentation lab, which we had for our 4 hours a week, but that was also used by a vibration group and another acoustics group. So we kind of had to keep our things in plastic boxes and pack them up. So, I mean, just a quick comment, you know, this is the direction in higher education these days. If you're lucky enough to be at a large university where you have fixed facilities, laboratories of one kind or another, count your blessings. The trajectory now is towards flexible spaces, okay? By which we mean all of the furniture's all movable, it's designed to teach anything there, and it's never empty, and it's very, very hard to set up anything of permanence, especially breadboards with components hanging off of them and so on. So you can imagine a scenario where everyone's got to pack their stuff carefully into boxes and take it out for the next lesson. Right. Okay. Just to give myself something to stand on here in terms of academic substance, what this is really about is experiential learning. Now, there's all kinds of academic theories about learning, different teaching styles, different methodologies, and so on. And they appeal to different cognitive models of how we learn. And there's a lot of very interesting stuff here to do with how memories are imprinted through the senses, whether or not you're an oral person who listens, or a visual person, and so on. But some things that are kind of missing, I'll just skip to the next slide actually, is things to do with touch, sensory things, and things to do with smell, olfactory. So in terms of, I'm sure all of you here have done plenty of practical project work. You've built things, you've handled things, but think now that many university students in these flexible learning environments, who are very cost-effective teaching, who use models for everything, all they've ever seen is animated GIFs of how this thing should work. They've seen the equations, they've seen diagrams, but they've never held one in their hands. They've never felt how heavy that thing is. They've never felt how much that hurts if you touch the wrong part. So, I mean, just being able to handle materials like mylar, the magnets, soldering irons, feeling the tension of winding the coils, and this may seem like, you know, beneath discussion and trivial to you, but it's a really vital component in a teaching approach. So many students had never put components onto a breadboard before. You didn't kind of realize that they had to explain, you know, these 5 rows, these are connected up. The smells. The sound has a fantastic ability to evoke very deep subconscious memories, right? So you hear a melody or something, and it can transport you back. At an even lower level of cognition is smells, which operate in such a subtle way, and yet, if you're never in the environment where you're in physical contact with lots of things, you'll never be exposed to that. So smells like, you know, doing the soldering and the glorious smell of an overheating transistor are all part of the experience. Right. Okay, in terms of sounds, it's great to have a theoretical understanding of the electronics and for acoustics and transducer design, but what if you've never really heard what different kinds of distortion sound like? Can you tell the difference between clipping and crossover distortion? What's the sound of the power supply unit failing when your voltage is getting down? And various kinds of noise and radio frequency interference. I had one student tell me, my microphone is so sensitive, it's picking up speech from the next room that even I can't hear. No, that's radio 4, okay? So, Actually seeing the traces on the oscilloscope, that's pretty nice. And here's a great learning outcome. Understanding the passage of time on a project, you know. How long does it take for a board to etch? How long does it take to get a 1 watt resistor from radio spares? Okay, so here's where we started. And literally I thought what we'll do is we'll do the original GCSE O-level tin cans and string experiment. But here's the difference when we do this at university level. We're going to consider the entire transducer system, including the plate as an edge-supported, center-excited, stiff membrane in terms of its area, the displacement that we're expecting of that for the given area. Then onto the vibrational modes of the plate. So typically we're expecting it to move in an umbrella mode, but let's look at some of the other frequencies that we might expect to see as peaks in that. Let's consider the conductivity of the cord simply as an acoustic channel, but as a vibrational channel in transverse and longitudinal modes, but also what it would look like as a string. So it's a bandpass filter. It's got a resonant center frequency. And then we've got that connected together with another system at the other end. And not even going into sort of mutual coupling and interaction between the two sides to build up a very quite difficult model of this to understand things like how energy might be radiated from the plate through the body of the acoustic cavity of the can at the other side. Okay, when you've thought about the model, now go away and do some measurements. So take your tin cans and string, either go down to the chamber or find a quiet place where you've got a signal generator, a recording scope, and pick some variables, string tension, I don't know, string length perhaps or something, size of the can, and measure the acoustic conductivity of the system in third octave bands. We've got some gear, I'll say a little bit more about the Flexus and things like that, but we were using ordinary laptops with reference mics and plotting these in Meth Lab. Okay, so what's the point of all of this? Trying to understand whole physical systems, thinking about what variables in that physical system will give different behaviors, predicting them if you can, and getting deeply into the measurement of the systems. Okay, so here's the brief there's 2 assignments, they're basically the same thing. If you pick an input transducer for assignment 2, you have to do an output transducer and vice versa. So look at the history of that transducer. So we went right back to kind of like Elisha Gray's water microphone. Just putting a rod into water such that a vibration would cause the rod to be immersed more into the water by a small amount, thus increasing the conductivity. Almost imperceptible signal, but it's there, the theory works. The water microphone is one of the earliest devices. Things like the hot wire microphone. Has anybody come across for a very specific resonant frequency, you get a kind of glass flask, put a hot platinum wire across the mouth of it. And literally as the air molecules are moving, so it's a velocity device. As the air molecules are moving, they're cooling the element. So as it cools, we have a decrease in resistance. Okay, do some design. For your chosen device, predict some physical variables from the material sciences. Think about the materials that you've got, and also practically where are you going to source them from, how are you going to machine them or cut them, work them in various ways. In the practicalities of construction, don't kind of design something that you can't build. And then build it. Document your process, show all of the stages and especially document the challenges that you face, things that have gone wrong in that construction. And don't be too fussy. This is not even a prototype, let alone a production model. It's something that I expect you to throw away at the end of the session and recycle the parts so that other students can use them maybe. Okay. Also, get to know the gear. So we'll start working on the bench with laptops, but eventually we'll take stuff into the chamber and use the NI gear to do some proper tests on things. Learn how to use the turntable for polar, for directional responses, how to set it up in 5-degree or 10-degree increments. And we're looking at these kinds of tests. So electrical impedance or reactance at various frequencies, sensitivity and noise. Generally, you can just do one test, do it at 1K. Frequency response, not necessarily always in 3rd octave bands. But various methods of taking these. So you can do a full sweep, or you can do an impulse, or you can do a sustained noise test. Total harmonic distortion of the device, if you're able to measure it, and any self-noise there in the system. We didn't have any liquid helium to really cool things down to see what the self-noise might be, but we managed to get some decent readings at room temperature. And as they say, if you go into any room, it's at room temperature. So, assignment 2, do exactly the same thing for your output device if you did an input device and so on. So this was the kind of some of the early stuff that we got. Just winding a coil around something and doing the guitar pickup. Now, lots of people were very keen on the guitar pickup. That was one of the most popular choices to begin with, partly because there's a lot of musicians who are guitarists. But of course, it turns out that although the guitar pickup is one of the easiest ones to do practically, from a theoretical standpoint, the guitar pickups is actually quite difficult, right? It's a change in a moving concentrator for the flux, which is pulling the flux out of the end of the magnetized pole as the string passes backwards and forwards through it. So it's not a typical variable to change, right? Okay, this is kind of what you'd expect for a design. First insight is you don't have to wind 6 coils, right? There's actually a way of factoring something out of this, so that's an interesting design efficiency to learn to begin with. Here we go. This is beginning guitar pickup 101 with a bit of SRBP, synthetic resin-bonded paper, something like that. Bit horrible to cut. Plywood is actually easier with, can file it down and stuff. And there's lots of kind of glue and mess going on here. The theme of this whole thing is glue and mess and things going wrong. This is all about stuff not working, okay? Right, we need some pole pieces. So here's a drawer full of bolts and nuts. They've got enough steel in them to be ferromagnetic, so there we go. We can put those through the plate, tighten up a nut on the other side, and we've got some potential pole pieces. Assembled with the back plate as well. Okay. Now, I can't remember what the ingenious thing with this was. These are all students' document photos. But somehow he had an app that he had managed to hook up to the drill to count how many turns that it had. So this is showing that, hey, I've actually managed to get 4,250 turns onto this, which is incredible. Because when we started, people were winding the coils and then they were boo-hooing and crying because they got to 300 turns and then snapped the wire. And of course, it's really, really difficult to do by hand. And eventually you snap the wire. And it's hilarious, but also pitiful to watch them trying to solder the enameled copper wire back together and then carry on. So yeah, that's very impressive once you've got a drill in your hands. Here's one that's been made under test. So it's clamped up there and going to be applying some changing magnetic fields to it. But, well, we needed a permanent magnet. Can you see kind of glued to the bottom of it is just a giant ferrite loudspeaker magnet. So who knows where the flux is going there? Certainly some of it's being concentrated up through the poles, but the rest of it's just flying off into in random directions. So then they figured out, well, actually what we need here is the flux running the right way. So we get some of these neodymium magnets and, well, epoxy them onto the bottom of the pole pieces. Have you any idea how difficult it is to keep two of those little creatures still next to each other for more than about 3 nanoseconds? There were some ingenious ideas here of drilling holes into a piece of wood, fitting the neodymium magnets in, putting the epoxy on and then holding them on and things like that, because otherwise it's really hard to get them stuck onto the bottom. But that one's kind of successful. A few of them are kind of moving around like loose teeth, but they're still hanging in there. And a test here being done with a solenoid hooked up to the signal generator instead of a string. So this is a kind of first test to see that the thing's working. And some other bits on the bench there that are kind of handy, a little unity gain amp, a little Genelec there so we can hear what's happening at the same time. Right, can anybody spot the horror? There's not very good contrast on the projector. Can anyone spot what's made somebody very upset here? Someone's managed to rake the coil, you know, and not just that, it's possibly split somewhere down several levels. So this one stopped working because it's been mishandled. And also, the whole thing is kind of pretty loose with these nuts tightened up. So it starts rattling around and very quickly becomes microphonic. So you're not just picking up the strings, you're picking up noises off the bench and so on. So what shall we do with that? Dip it in some wax. Those of you that are old enough to have taken apart radios in the 1960s will remember pretty much everything's covered in this amazing wax to stop the microphony of components, which is why television sets used to burst into flames, which was so much more fun and so much more environmentally friendly. I don't know if you know the stuff that they use these days. It's kind of fire retardant. It's evil stuff. It's absolutely horrible for the environment. But good old wax candle in a basin there, getting melted. No health and safety precautions going on here. But once we dipped the coil, a fair degree of protection for the coil and reduction in vibration. Okay, moving on to some of the other groups, was the carbon microphone. Really easy to do if you can get hold of the carbon granules. So it turns out the best place to get them is fish shops, not fish and chip shops, pet supply shops, where carbon granules are used to filter the water. They're available in several different kinds. Activated, large area varieties. Nothing against Chinese products in general, but don't buy the Chinese ones, which kind of are mixed with some kind of, I don't know, nuclear waste or something that they're trying to just sneak out of the country. They don't work at all, and we could never kind of figure out quite why. They seem to be unusually heavy. The cheap ones were the best, the non-activated cheap ones that look like sort of gunpowder. They're very hard. We discovered that we could change the surface area by crushing them more. So a big, heavy pestle and mortar was great if you wanted to sort of smash these down. Best to wear a mask as well, because they throw off quite a lot of dust while you're doing it, so very fine carbon particulates. But once they are crushed down, you can get some really good results. So this is one very early prototype. This is two plastic cups from the refectory, a little bit of aluminium foil in order to create a base and a top. And we just push one plastic cup into the other. And that was giving us around about 1 or 2 millivolts of difference dropped over a 50 ohm load or something like that, I think. Okay, this is them trying to take it to a slightly more robust stage. So Pringles cans, they're very interesting, useful things, especially for RF work, but also for building things like carbon mics, where they're metallized on the inside so you can get plenty of connectivity to your carbon load. And then I think that's just aluminium foil over the top. Now, you probably think aluminium foil is much too heavy for a diaphragm, but the way that they test these things is they shout into them, right? So there's some serious pressure changes going on there. Elastic band there holding it in place. I don't know what the point of that last one is. Talking of smells, when you're trying to drop 60 volts, 30 volts across a load of carbon without any current limiting, a 1/4 watt resistor is not the thing to use, okay? So I don't think they'd seen any action in decades. Thank you. So these are decade boxes with the big clunky switches, perfect, really good. So you can set up a load to drop that across. And here we go. The downside of the carbon mics is that when you take them into the chamber to test, you also have to take the power supplies with you. So we had lots of trailing cables, and here's a mic kind of very professionally attached to a chair there to be measured. Okay, a little bit of data from that. Absolutely wonderfully flat response, particularly if you can't see, these are millivolts. So we doubled that, maybe more than that, maybe 6 dBs of difference. Just kind of one frequency, really, and not much else happening in the other places. They're improving their measurements as they go as well. So part of the formative feedback is me looking at how they're doing stuff and saying, what are you actually measuring here? And is this working? Okay, a very slightly different take on the carbon granule mic is this carbon rod mic. So these are 2 steel beams, and then the carbon rod is sat across it. And as pressure increases on the rod, the surface area goes up, and we get a resistance drop. So this design here, I think, was kind of slightly modified or borrowed from somebody's blog article, a Maker article. It's a trebuchet microphone. So you can see that this is a pivot here on this bottom beam, and the diaphragm here pushes this piece of tube against. So there's the bar, and there's the fulcrum there, and the bar here is pushing contacting this top beam just by the pressure of being held by the diaphragm. And there's incident acoustic energy on the bottom diaphragm there. We actually got quite a respectable signal coming out of that. It needs a transformer, so here's one. Nice bit of PVC pipe, couple of 100 tons of wire, and some, I think it was about a 10-to-1 step up or something. This one here is a rather clever capacitor mic. Now, almost none of the condensers worked at all. The students had real problems with the condensers, and it wasn't the voltage. It was getting the plate separation small enough. There's almost no way to get micrometers of difference in a kind of in a casual workshop situation. And this young lady came up with this scheme here with, you can't really see, this is rubber, which is holding the charged, the other side of the plate is some metallized plastic stuck to the back of the rubber. So it's very resonant, but it kind of holds it in a fairly stable place with plenty of tension here. And then what she's done is put some grub screws in to push the back plate up closer and closer. And she was just tightening them up until it shorts with a very low voltage, and then backing it off, and then tightening up until it shorts, and then backing it off. And so that way she was able to just position it so it was almost shorting, and then talk into the diaphragm and get a result. So that was pretty good. Okay, what went wrong here Well, basically there's a little bit of potential for radio frequency interference in this, because we just got these leads trailing across the bench coming up to this capacitor microphone, which was not a great example anyway. So off you go and build yourself a single stage FET amplifier and put that up nice and close to the diaphragm so you can get a boost. So there's a nice opportunity there to learn some practical electronics as a solution to a problem. Okay, and that's actually working. We're getting a signal out of that one. Here was a weird one. There were some groups that just couldn't decide what to do, and I had a project that's kind of in the background at the moment. Josh Rees suggested that we might look at why different liquids sound different at different temperatures due to microcavitations, is my theory. So I think we're just tentatively playing around with thermoacoustics at the moment and the opportunities for measuring temperature by sound, which is kind of possibly something very useful in situations like where you can't put metal or you can't put sensors into that situation. So what these guys have done is built some acoustic permeability probes. They're just big forks with piezo discs on them. But their objective is to minimize the crosstalk in the system. So here they are testing some. And lots of pages and pages of tables like this that they came up with, different material properties, whether they would melt, whether they were, what kind of acoustic vibrational damping that they had, and so on. Okay. And here they are testing these with the largest lump of steel that they could find from the physics lab, just put in the middle there as an obstacle, so that we're hopefully just measuring what's traveling around the fork as crosstalk. Okay, right. This it was a page from a student's report where he's copied out the full industrial process for manufacturing piezo crystals. This is the Meth Lab version with sodium. What do we need? And we need a double salt, a sodium potassium tartrate salt, I think was the. So we needed to get sodium carbonate and tartaric acid, mix them in the right ratio, and when it's really saturated, cool it as slowly as you possibly can. And that lovely specimen there, that was the one he chose to use. You can see. It's not very robust, as you can imagine, so it's quite easy to accidentally crush. But here's the crystal fitted to the back of the baked bean tin. So this is acting as one of the electrodes, and what he thought would be a directional kind of cavity. Transformer on the back here to decouple it, and off you go. So there's the incredibly flat frequency response for that one. Nice bit of action around 6K. But surprisingly, he was kind of expecting this to just drop down here, and it just kept getting better and better and better. And I think our signal gen only went up to like 20K, but it was loving it. I think it would have gone up to 40 or 50. So very, very good high frequency response for those. Okay, not so directional. Bit of a mess, really. Basically, that's the polar response of a baked bean tin. Okay. Most of the groups decided to make a paper plate loudspeaker, and you can get some pretty good, quick results with this. We found a tampon tube. Cardboard was a great former, but it was a little bit too heavy. So many of the students just wrapped a piece of paper, a little bit of acrylic adhesive, and then wound onto that. And by the time you've got 100 turns over it, the coil keeps it together, really. Okay, so it's glued onto the back of the paper plate there. This is a typical early one. There's two embroidery hoops there. Some bits of dowel holding them together, and bits of tape over here for the suspense. Flux lines, question mark. So it took people a while to figure out these neodymium magnets are cylindrical and the flux lines are coming out like this. There's nothing to concentrate them across the coil, so they're not actually, it shouldn't work, right? It shouldn't work. The flux lines are going the wrong way. What makes it work is if the magnets are low enough of the flux lines are fanning out and then crossing the coil. So as you can see, they're kind of suspended on something and then they're held back. There it is in the chamber, undergoing some tests. And, oh, it's looking good. There's a bit of 2K there. Not much happening down here now, and pretty rapidly falling off above about 4K. But it was amazing to hear. I mean, this is the win for this, is when a student who's never built something like this before connects their iPod up to one of these and starts hearing music coming out of a paper plate. We should be doing more of this at O-level, we should be doing more of this at A-level, but the fact that it's happening at university level, it's still great, you know. There's a lot of happiness doing things like this. So as you can see, what we're doing at university level, even though it's a paper plate loudspeaker, is subjecting it to proper acoustic tests. And this is the real area of learning, if you like. Although we're having a lot of fun playing around with silly tin cans and strings, we're then using those in a proper measurement situation and getting some really good learning outcomes about the measurement gear, about the effects of changing different variables and so on. Okay. So there's our loudspeaker, paper plate loudspeaker. Not surprising that we've got a kind of figure of a kind of it's a radiator really on both sides. Now, the one thing that saved us is that we finally got access to the 3D printer. And here is a basket designed in the 3D printer and fitted with 3 neodymium magnets. Until that point, several of the baskets that the students had made for their loudspeaker designs were actually baskets. They were hanging baskets from B&Q, which are a lovely wireframe thing, and they're great because you can, you know, weld stuff onto them. And but then the 3D printed one was a big opportunity. So as you can see, there's 3 neodymium magnets sat in there, and by this time they'd kind of learned about the way the flux lines were going on these magnets. But this is kind of quite an ingenious design. You put one in the middle to pull in the flux from the other 3, right? And then situate the coil right in the middle of that. So the coil's floating above it. And it was actually pretty effective. Although this looks like it's covered in tin foil because of the photograph, it's actually papier-mâché. So, you know, we were looking at various methods of designing cones, whether they were kind of conical folded or whether they were cast and stuff like that. So, as you can imagine, it's a lot heavier than we'd want it to be. But at least they're starting to investigate proper kind of commercial production methods, albeit in a very toy way. So this is actually a rubber surround here, made from a bicycle inner tube, cut in different places, in different ways. Okay, not great, but there you go. At least it's getting tested in the lab properly, and these are the real results coming from it. This is just probably because the coil's got no spider to hold it there. So it's wobbling around like this. The whole assembly's just moving. This is one of my favorites, actually. It's a planar speaker design, which was originally designed to be built, I think it was on a 64 bed of small magnets. I think he went for like a 5x5, a 25 in the end, because it's just too many to fit. So this drilled back panel, and then this is a piece of mylar. Was it mylar? Or some kind of stiff thermosetting plastic. I've forgotten what it was. It was like a tape, and it was covered in copper. So it was adhesive on the back and copper on the front. And then he used an etch resist pen to etch this out. So there's the theory for it, of how it's going to sit in the field. And here we go. This is with the photoresist put on with the pen, then etching it in the ferric chloride, and then placing this over the matrix of magnets. Not too shoddy, right? Well, this part here was great, I thought. That's actually from, what have we got? 700 to 5K maybe. Not bad. It's and then it's just crazy up here and nothing happening down there, but quite nice. Here's another favourite of mine. This is parabolic design, and learning that parabolic is different from just a bit of a hemisphere cut off. You know, focal point for that, it's no good. You need a parabola, right? So how do you get one? Well, good idea is to design one in a CAD package and 3D print it. And this is a design for a handheld parabolic. There's the strut here. It's going to hold a little MEMS microphone or a little micro electret from a telephone handset or something. And there's a grip to hold it up. Not a bad polar response there. It's what have we got? I can't really see these very well. It's a bit blurry, isn't it? 400, 1200, I think. I'm not sure. Sorry about that. The slide's not very good. That top one's a 20K though. You might recognize that that's an attempt at a ribbon microphone. And this was the best performing piece of hand-built gear that we had altogether. He said that he plugged it in, heard we do some music for a test, couldn't believe that what he was hearing was the mic that he had made, had to go back and double check that he hadn't actually put something into a wrong channel and was still not using the reference mic or something. It just worked first time and sounded amazing. So sometimes this happens for no great, well, not for no great reason. He put a lot of work into this, which is 3D printing a clasp to hold the folded ribbon for the motor assembly. And then a decent preamp up nice and close to it. So this is a transformerless design, but it's just kind of a nice op amp there. So make sure, and also with a balanced output. So we got to put that into a proper, and there's the, what have we got, at 1K and at 10K. Well, it's all over the place at 10K, but there's a response that we'd expect around about 1K. Okay. So it's kind of pretty much it. I'm going to wrap up. Here's some few last comments. It's amazing what will actually work. This was a SETI thing. I've forgotten whose formula it is about whether there's likely to be life in the universe. And at the first approximation, it's like, nah, we're just on our own. There's no way there's life out there. But when you kind of actually change a few of the variables, you think, well, life is actually inevitable. You know, the problem is that it's almost absolutely certain that there's life out there, you know. And there's the same kind of thing going on with this. Is to make an actual loudspeaker that performs well is really, really, really difficult. You know, it's probably beyond the capabilities of a bachelor's engineering student to do well at all, even with some good manufacturing gear. But just put a magnet near a piece of wire and it's hard not to get a sound out of it. So there's a very wide range of possibilities there to experiment within, to find little things that just work. And then you can develop them. Once you've got something working and you've got a signal out of it, that's something to keep on pushing ahead with and seeing if you can improve it. So there's amazing learning opportunities. 3D printing, absolutely amazing for teaching because, you know, if you got an idea that this could be really time-consuming to manufacture in other materials, and you just want a use-once prototype case, make it, see if it will work. Obviously, the nylon materials are rubbish for anything that gets hot. The number of designs I've seen that melted as soon as you cranked up the power a little bit. Okay, equations for real systems are bad. They're really hard, okay? So even once you've got just a few physical couplings, some springs, some plates and things, difficult stuff. Now, Jeff has written a book for us, which I'm going to be recommending to the library. Jeff, what's the name of your book, of your text? Would you like to share it with us? I'd like to make a little plug of Jeff's book.
Focal press.
Is that okay for me to do this? Okay. Coming out with Focal Press in October. Jeff Hill's loudspeaker design, modelling and measurement. And this is full of the kind of detailed stuff that that I would really have loved my bachelor's guys to have looked at. Plenty of graphs, measurement, designs of the various components of loudspeakers. So one for your library. Okay. Nothing is ideal. When you see in physics books, the ideal, that word means it won't work like this. Yeah? Okay. Don't give up. Absolutely. I was disappointed by the lack of persistence in many bachelor students these days. They'll have a go. It didn't work how it said it would in the textbook, and now they come to me and they say it didn't work. You really need to keep pressing, keep on trying with that. Did you get any signal out of it at all? No? Well, yeah, okay, well, there's something to work with, right? There's something that you can try changing a few variables. More windings on the coil. Push the parts closer together. Maybe you need a transformer. Maybe there's an impedance problem there, okay? So definitely a strategy to encourage agile type iterative engineering design. Off you go, build it. Does it work? No, great. Figure out why, come back and show me something that works better. Okay. Soldering irons get hot, and neodymium magnets are very, very, very strong. And they're so strong that if you pinch them together, they'll give you a little blood blister, and that really hurts. So I think we're done today. The student experience, very, very positive. They loved this. Many of them said it was the best part of the course, even though the theory was good, but the getting down and playing around with materials and trying to build the stuff was actually really inspired them. So some of them then wanted to go off and become design engineers, and if they weren't into hobby electronics at the beginning, they were afterwards, and many even said that they considered working in electronics design in some way. Some thank yous to Frank Noakes at the Solent University's Solent Acoustics support team. Frank was just amazing getting bits for me, so I didn't have to keep ordering stuff. And Colin in the engineering design block, who was able to help us with 3D printing and with some laser cutting, which was great. And to all the other support staff. Thanks very much to those guys, and thanks very much to you guys for listening tonight. So Charlie, has anybody got any thoughts or questions of any kind?
I mean, I was quite curious as to the sort of bit you were touching on at the end, and how keen were they actually to? I know you were saying that they tried one thing and then they stopped, and I know from my experience that it can be very frustrating. But how keen were they to take their projects home and do it? And do you think there was anything else you could have done to? Yeah,
of 20 students, there were definitely maybe 5, I would say. So 5 students were saying that they wanted to carry on with this, and could they keep their projects to keep on developing them, and that they wanted to use them as part of another project later on, and continue improving them. So,
is there a specific sort of microphone or transducer design module in the level 6 that they could go on to? Is that part of the master's program, or?
Unfortunately not, because so the live sound guys were then going on to do more sort of OBU and things like that. Who do we have? There were several streams, so the course actually catered for several streams. There were the acoustics measurement guys. Most of their level 6 material, I think, is really around sort of abatement and field measurements and stuff like that. So they didn't really have an opportunity to take it further in an academic situation, which is a shame. But they were keen to do something as a hobby. Yeah.
I was actually so I was actually going to quickly say I was actually at a course revalidation for Ben Mosley's course recently. The subject came up of how possibly AES sustaining members or even industries could get involved with something like that, and it kind of sort of started clicking together that maybe I could unload all the bits in my workshop I don't want on courses like that. That might be a good route to getting some more money.
So that's a very good idea, Charlie. We did have some pledge. We have had help pledges. So PMC gave us some scrap cabinets and some bits of, and also one of the pieces that they use for demonstration, which is a cross-section of a labyrinth cabinet, so that you can see how it's constructed inside, and they use that for their trade shows to show how their work's done. And that was a really nice instructional piece. I suppose the kind of things that we need are bits of semi-assembled loudspeakers, especially things like baskets, spiders that can be removed and put back. So things that could be used almost as a loudspeaker kit, that would be great to sort of show how one is really made. It's very difficult, though, with very small things like MEMS microphones or miniature electrets, because there's nothing to see unless you've got a big lens or a microscope. It's just a tiny little thing on the end of 2 wires. So that's kind of where the big embroidery hoops and the foil balloons came in, because it might not work like a very good condenser microphone, but it certainly looks like one, and you can see the physical operation of it. Yeah.
Thanks very much, Andy. Given that you've taught the course this year, what are the things that you're going to be changing for next year?
Possibly one of the things that's changing for next year is me. So this is my opportunity to document what I thought was a very good course with some good outcomes that may not necessarily run again the same way. However, if they ask me to work on this course, again, I think just my own preparation in terms of materials. I think we could spend maybe 50 quid up front and just have a better set of adhesives, maybe some things like felt. I'd really like to keep it, the whole fun of this and why it worked was that it was fun, it was low budget, it was make a mess, have a laugh and do something. I think if it had been, there's so many ways I could improve it, right? And using better manufacturing techniques and something. But the story of this, the story here tonight is that it worked because it was crap, right? It worked because it was fun. And I think the learning outcomes were actually boosted by that was in my kind of abstract for this, which was just a load of geeky gags, wasn't it? It was like a shoestring theory of teaching physics. And there's something to be said for how constraints increase creativity and focus. Yeah. So maybe I'd leave it more or less the same. It's a good question. Right. Yeah.
The one thing I would say is don't forget the power of using modern CAD tools, especially things like Fusion 360. You can tie that directly into the 3D modeling later on. And so if you want to show something like a loudspeaker, a MEMS microphone, anything like that, you can build the model up. And I'm pretty sure that all of your students will be more than happy with computers nowadays.
Yeah.
So they're going to be completely into that. And then you get the link between that and the real physical world.
Yes, thanks for that, Jeff. Just in case that didn't make it to the tape, Jeff's suggestion is don't forget the power of modern CAD tools. I can take that comment on 2 levels. Those tools are very powerful as pedagogical tools for me to make models in to then animate and show the students. And also for them to use to build things to then try and manufacture. The practical problem that we had with that is a lack of a uniform platform that was available to all students. So Blender is the one that's... What are you suggesting?
Fusion 360, there's free open source
Yeah.
software tools that will do everything that you need.
Which one's that?
Fusion 360 is
Fusion.
Autodesk, download it from the web, won't cost you a penny.
Yeah.
Magnetic modelling, FEMM, ditto.
Jeff, you're going to have to hit me with a list of modelling tools to use. Okay. They're all available in the book. Okay, they're all available in the book.
There's links to them all.
Thank you for that. Super comment. Super. Anything else before we hit the pub?
More? Well, thanks so much, Andy, and thanks for battling this rock band next door.
That was great. It
You
made me
did
feel
really
like,
well.
feel like I was at a festival.
I think that's it, and for anyone that's hanging around, we'll go to the Shakespeare's Head, and thanks again to Andy.
Cheers, guys.